Hi and welcome to this film which is about covalent network substances. Now if you've been watching the other films about covalent compounds, you'll have been looking at covalent molecules, and we call molecular substances ones where you can easily describe the smallest repeating unit as the molecular formula. With covalent networks, these molecules just go on and on and on, so how big the molecule is or how many atoms it's got in it really depends on how much of the substance you've got. So we call these kind of substances covalent networks, and they've got different properties to covalent molecular substances, and it's important to understand why these differences arise. So hopefully by the end of this film you'll know the names and formulae of all the covalent networks that you might be asked about in an exam or a test in year 11 and 12, and you'll know how the structures of these three different kinds of carbon, or allotropes, differ from one another, and why that means that these different types of carbon have different properties from one another. Okay, here are the covalent networks that you should be able to remember. Okay, if anything else comes up in a test or an exam, then they will tell you it's a covalent network if they want you to know that. But these ones are important to remember. So we've got two very important forms of carbon, graphite and diamond. We've got silicon, which is also in group 4, just like carbon, but there's also other group 4 or group 14, I suppose we should call them nowadays. Group 14 elements might also be expected to form covalent networks. Silicon carbide, which is just a compound of those two that we've talked about already, and one other example, silicon dioxide. So if you can remember those, that'd be good, because they might ask you recall questions about them. Any other covalent network, they'll introduce it as a covalent network before they start asking you questions about it. Okay, let's try and understand what we mean by allotropes. We've been talking a little bit already about the allotropes of carbon. The definition is an important one, and here it is. Different structural forms of the same element is what we mean by allotropes. Carbon's often used as an example of allotropy in year 11 and 12 chemistry. So there's two I suppose these are the most important ones. You do sometimes see questions about buckminster fullerenes, but not all that often. I mean, really and truly, if you were stuck and you didn't have time to revise them all, you'd definitely go for those two. They're the most important to know about. Okay, here we go. Here's a look at how they're different and also why those differences give rise to the properties that these substances have. Okay, let's look at graphite first of all. Now, if you look at a typical carbon atom in a graphite structure there, I say it's typical because most of the atoms will be like this one. They won't be at the edge like these ones are in a typical piece of graphite, bearing in mind there's millions upon millions and millions of atoms in a visible piece of graphite. So most of them will be like that one. Have a look here. You've got carbon, which is in group 4, which means it's got 4 outer shell electrons. Okay, that means it can share electrons to form 4 covalent bonds. But each one of these atoms has only formed 3 covalent bonds. So there's 3 bonds to each carbon. They're strong. Covalent bonds are always strong. So are ionic bonds. Okay, but in between the sheets, because you've got this spare electron that carbon hasn't yet used to make bonds, those electrons can kind of float around in between sheets. They'll create these things called van der Waals forces, which you need to know about in year 12 but not yet in year 11, and they'll be coming up in a separate film. But they can also move, so that enables graphite to conduct, right? Which is very unusual for a non-metal. Mostly it's just metallic substances that conduct, or ionic substances that have been melted or dissolved. But here's a non-metal that actually conducts. In addition, it's very soft, because although we've got very strong bonds within the layers of carbon atoms, between those layers the forces are weak, so they're easily broken. And what's more, one layer can slide over another layer, so it's a very slippery substance. Okay, so we can use graphite as a lubricant. It's a very common use of it. It's found in oils and greases and other forms of lubricants in industry, basically to stop two surfaces grinding against one another, because the sheets can slide so easily. Okay, so 3 properties of graphite, very important there. It's got a high melting point because in order to melt it, in order to get all the atoms moving around freely, you've got to break very, very strong bonds. Okay, so there's the structure of graphite and how that relates to its properties. Let's move on to diamond now. Now here is, this is a very, very difficult thing to draw compared to graphite, but here's a typical diamond atom. That is to say, it's not at the edge. Okay, only a very small proportion of the atoms in a diamond will be at the edge, and they won't be typical like this one. They won't have 4 bonds to each carbon. 4 bonds to each carbon means that you don't have any spare electrons, right? Because all the electrons have been used to make bonds. That means that this substance is an insulator. Okay? There's no spare electrons. It's an insulator. It doesn't allow electricity to flow through it. There's no charged particles anywhere that can move around. Okay? In addition, it's extremely hard. It's the hardest substance we know. And that's because, unlike in graphite, where there were weak forces between sheets, all these atoms are joined together by these strong covalent bonds. There's none of these weak forces around. So diamond is extremely hard. It makes it very good for use as a cutting tool. So if you've got a blade that you want to cut through stone or something like that, if you embed diamonds in the surface of that blade, it will cut through the stone and it won't go blunt. Okay, but it's an insulator. It's got also, just like graphite, it's got a very high melting point. About the same, really, I suppose, in the grand scheme of things, around about 3,500 degrees. And once again, the reason that its melting point is so high is because you've got to break those very strong covalent bonds. The last form, and I suppose the least commonly seen in exams and tests, is buckminster fullerenes. Now these are kind of, I suppose, quite a recently discovered form, certainly compared to graphite and diamond. But again, we've got the same element here, carbon, but in a very different structure. It looks a little bit like a soccer ball. So you've got these kind of pentagons of carbon atoms surrounded by hexagons of carbon atoms and then other pentagons as well. And here's just another way of seeing it, except that this one is a ball shape, this one's a tube shape. Okay, so this is actually called a carbon nanotube, and this is called a buckyball. Okay, but what you can see common in these two structures is that once again you've got typical atoms, right? Typical atoms that have only formed 3 bonds. Now if they've only formed 3 bonds, you would expect spare electrons. Okay? Now a ball isn't going to conduct electricity very well because it doesn't make a very long wire. But if you can make a tube out of millions of carbon atoms, it's going to be practically invisible, but you'll be able to conduct electricity down it. So we'd expect these things to conduct. Okay? We wouldn't expect them to be soft and slippery like graphite because there's none of these layers that are held to other layers by only very weak forces. We'd expect them to have high melting points, just like graphite and diamond, because there's same bonds here. Okay? We've got to break those bonds to melt or boil these substances. Okay, so that's about it for covalent network substances. Make sure you know all the examples because they can ask you to remember those, and if there's anything outside of those, so there are other network substances, but in a test or an exam they're going to tell you that that substance is a network. And I suppose just to summarize, okay, so that's all the covalent substances covered now. Just remember that a covalent substance will always have non-metals combined together, okay, and the network covalent, so you can assume that pretty much all of them are molecular. The network covalent ones, they are the ones that we saw on that earlier slide. Okay, there they are. So remember them.